So, welcome to this presentation about InSAR Svalbard. This is a development project that we just kicked off. Me and Lynn will tell you a little bit of what we aim to do to define this upcoming operational ground motion service for Svalbard. So, what is the relevance of a ground motion service on Svalbard? In a permafrost landscape of ground is moving. It can be frost heave and thaw subsidence in the flat terrain. And it can be, we can have various slope processes in the slopes around. This can have a direct relevance to the society in terms of stability on infrastructures, as you can see here, or in terms of geohazards, for example, rock slope failures that have caused many fatalities on the mainland over the last century.
Maria, I think we cannot see your screen actually.
You cannot?
No.
Oh.
I was not sure it was me who misunderstood how to.
No. Yeah, it looked okay here. Okay, let me. What about now?
Yes.
Yes. Perfect.
Maybe good to start again.
Thank you. Thank you for stopping me, Lynn. That was okay. We can start from here. So what I was saying was that in a permafrost landscape, the ground is moving. We have frost heave and thaw subsidence on the flat ground, and on the slopes around it, we have various stone slope creep movements that can have a direct relevance to, for example, stability on infrastructure or geohazards such as rock slope failures. So now we are where we started. Common for these processes are that they are controlled by climate, by temperature, by precipitation, ice content in the ground, and as an indirect relevance of this is that the dynamics of the ground can tell us something about the environmental changes. And again, in the permafrost landscape, we have a variety of different landforms. All of them are moving at different rates with different temporal behaviors and with various directions, as you can see here. For example, we can have ice that forms and melts on the flat ground that may cause upward or downward movement, while on the slopes, here in blue, rocks, sediments tend to move down the slope as a combination of horizontal and vertical components. And as I said, all these movements are influenced by a large set of environmental factors that can control the distribution of the landforms and also their temporal behavior. So in the context of a climate that are changing, it can give us an indicator of a changing environment by measuring these movements. And this is of interest to understand how the cold regions now are currently evolving. So how do we measure these movements? As you probably know, there's plenty of available instruments and techniques to measure these movements. But what we're now aiming to do is to capture the dynamics of larger landforms or more regional scale. And this is where remote sensing comes in. And here we are talking about InSAR. So I will go through a little bit of InSAR basics with you to tell you about how we can capture these ground movements. So InSAR is a technique based on images that are acquired from an active microwave sensor called the Synthetic Aperture Radar, or SAR, that are mounted on satellites. These satellites, they are flying around the globe, as you can see in this little animation here. They are flying around the globe with a polar orbit and takes images of the Earth's surface. And eventually these scenes covers the entire globe. These radars, they are active and transmits a signal and records back the echo after the signal have been backscattered by the ground. But a SAR can only measure movement in one dimension, so either towards the east or towards the west, depending on the orbit, if the orbit is ascending or if it's descending. So when the signal reaches the ground, as you can see, 2 seconds, as you can see here, as it reaches the ground, it does so with a certain angle to the ground. So to detect displacements, we compare 2 or more images. These images are acquired at different times. And between 2 images, a landform moves with a certain displacement. Then the distance between the sensor and the ground is changed, and that is what we detect. We detect the phase shift between the 2 radar signals. But as mentioned, a SAR instrument measurement is one-dimensional, and one should know that it detects the displacement here with the red arrow is only a projection of the real displacement along the line of sight of the sensor, which means that in this case, InSAR is detecting an increase in distance between the sensor and the ground, but also slightly underestimates the real displacement because the orientation of the real displacement deviates from the line of sight of the radar. And by measuring changes over a whole landform or over a landscape, we can then map the spatial variability of the ground movement with millimeter to centimeter accuracy. And then by adding several of these images and combining many image pairs, we can provide time series that documents the temporal evolution of movements during a season or between years, depending on which process we are looking on. On the mainland Norway, we launched a ground motion service in 2018. One of many uses of it is to identify, map, and monitor unstable rock slopes. As you can see here, they clearly stands out in the map as the red areas. And in the graph here, with the release of the nationwide data set, this is a graph that shows the number of unstable rock slope that we are mapping out at the Geological Survey of Norway. And with the release of the nationwide data set, we clearly see a jump in the number of unstable rock slopes that we could identify. But we also see many other uses of InSAR, not only on the natural terrain, but also urban subsidence. And today we have approximately 100 to 150 daily uses of InSAR Norway. So yeah, it's been very beneficial to many users on the mainland. Apart from, in addition to InSAR Norway, we have the European Ground Motion Service that delivers InSAR data, not only at the national scale, but at a continental scale. But as you can see here, Svalbard is missing still. So I will now give the word over to Lynn, who will talk about some of the challenges and some of the reasons that we need to handle Svalbard and the periglacial permafrost landscape a little bit different than we do with these other ground motion services.
Right. It's a bit back and forth between presentation as we are sharing this seminar with Maria. And the idea is now that I explain a bit why basically InSAR Svalbard has not been covered yet by a ground motion service. And there are actually two main reasons for that. One reason is that there are really different technical challenges that require other processing strategies in Arctic environments. Because the processes are different, because the conditions are different, and the limitations then are different. So for now, it has been left aside, and we wanted to have a separated project to really design something that makes sense for Svalbard. And then the second part is, of course, the different needs and the different user communities in Svalbard compared to the mainland, that also require other product types, so that we wanted to take time to define with you, with people really that will use the data, how we design such service and which kind of product we can deliver. So basically, we need products tailored for Arctic conditions and valuable for end user, which sounds a bit obvious, but that's a bit of a trade-off strategy or analysis. Basically, what can we do and what do we want? And sometimes it's not the same, so we will have to make choices. But obviously, we aim for having something that makes sense for the end users. So that what we're starting now is a dialogue between InSAR experts and end users. Also the goal of this seminar. And now I will explain a bit why the first part of it. Of course, the second part, that's something we need to discuss with you. But the first part related to technical challenges and explain why Svalbard is different. So one element is that when we use InSAR for mapping, monitoring ground movement, we have several common limitations. So it's not especially related to Svalbard, it's everywhere. We typically fail to retrieve information on dense vegetation when it's in temperate regions. This is not a problem in Svalbard, right? But there are also challenges when the ground position is changing really suddenly, like in this example here, the picture A. And if it's too fast or changing too suddenly, we lose the stability of the interferometric signal, and that can we cannot retrieve information basically. Another big challenge in cold climate regions is the snow. So when there is snowfall, especially when the snow is wet, we also lose stability of the interferometric signal. And a third example of this limitation is when there is surface water. So typically on lakes, on sea, it doesn't work. But in addition, as you know, typically in Advandalen or other big valleys, at the beginning of the sowing season can be really wet, and that's also a challenge for retrieving ground movement. In addition, so we have a relatively short snow-free season in Svalbard. So if you see the red part here in these figures, this is what we consider as the InSAR observation window, considering that InSAR doesn't work on snow. Which also is a challenge for processing. This is also a challenge on the mainland, but of course in Svalbard, the season is shorter. And also in the mainland, the processing chain is based on an algorithm called persistent scatter interferometry, PSI. And this is typically designed for slow movement, rather linear processes, and also ground targets with relatively stable conditions, which in Svalbard for many reasons it's not necessarily true. Due to frost impact, the movement patterns are different compared to temperate environments. So many parts of the terrain, as we can see in this first graph here, are affected by cyclic patterns, subsidence and heave, as Maria explained before. And also some landforms have major seasonal acceleration during the sowing season. And that also require different processing strategies compared to the mainland. So basically, which kind of data or which kind of InSAR product can be actual for Svalbard? And here I will just show a couple of examples of what we have done in the past. It is not exhaustive, and it is not meant to say that this is what we will necessarily do. This is more to show examples and to discuss then how we can design a ground motion service in Svalbard in the best way for the users. So if we consider separately, let's say, the slopes and flat terrain, because the processes are pretty different, we can design different kind of products. Typically, if you consider mountain slopes, you have different creeping processes. Here it's an example of a rock glacier, but we could also think about rock slides, right? Solifluction lobes, other moving landforms. And what we can be interested in here is to know where it is moving, how much it is moving, and how it changes during a season. Typically for a glacier, it tends to accelerate throughout the season, but also how it changes between years. And typically for a glacier, it has been shown that it tends to accelerate under warmer conditions. While in flat terrain, so as also Maria introduced, you have this cyclic patterns at the seasonal scale due to active layer freeze and thaw, and the ice formation and melting in the ground. So you can have an information about subsidence and heave patterns. And then, of course, if we manage to connect the years, you can also have an information on how it evolves interannually. And if there is a long-term subsidence pattern, it can indicate permafrost degradation. So to show some of this kind of product here, so imagine that the radar is taking an image from the above, and throughout a season, at one point the ground is completely frozen, and in early summer it starts to thaw in the upper part of the ground. The active layer is starting to thaw, and at the end of the season, the active layer is totally thawed, and if there is ice in, or if it was water ice in the ground, the difference of volume between the water and the ice leads to subsidence. And then when it refreezes, it will heave back in a perfect stable environment, let's say. And if we take just an information on how where it's moving, and just an information about the spatial distribution of this kind of processes, so how much it has moved during the summer, you can have a distribution of the subsidence level. Here it's an example in Bredal, for example, and you can see that there is a large variability of amplitude that is related to how much ice there is in the ground, and also related to which kind of sediment is able to actually segregate ice. And also, so that's the spatial distribution component, and then of course we are also interested in the temporal evolution of this kind of pattern. So, but if I continue just briefly on the spatial component, so InSAR can then be used as a mapping tool, first to detect where it is moving, and potentially also identify objects that can be a hazard close to settlements, for example. It can also become a supporting tool for geomorphological mapping, because we can see that there is a relation between the amplitude of the movement and the type of sediment, typically in valley bottom. Here, sediment that are fine-grained tend to have a higher subsidence rate, because they are more able to segregate ice. This is a bit of a simplification what I'm saying, but just to show some examples. And then of course you can try use InSAR to categorize different landforms and processes. Now, if you now think about the temporal evolution of these displacement patterns, so you can retrieve time series that looks this way, where it subsides at the beginning of the sowing season. So before it was frozen, it was snow. Maybe we missed something at the beginning because it was still snow. So it doesn't mean that nothing happened before. We cannot measure. There is snow we cannot measure, basically. And then the ground is subsiding, and at one point, the ground starts to refreeze, and there is a heave pattern due to ice formation. And by comparing this kind of displacement pattern with what we can measure in borehole temperature information, we can see that it fits quite well with, so this graph here in the middle is a surface temperature, while the graph on the top is a temperature at depth in a borehole in Bredal. And we can see that during the first part of the season, the active layer is thawing and the ground is subsiding quite quickly, while from August in this specific year, the active layer is as thawed at its rather at its maximum. It continued to be high temperature, but it doesn't propagate much more, and then it's slowing, the subsidence is slowing down because it doesn't melt much more ice, basically. And then at one point the ground is freezing again, and then you have this heave pattern that starts. So InSAR can be then used as a tool to document the ground thermal regime. It's an indirect tool, but it can still be useful for different scientific application, and also operational application when you think about infrastructure stability, for example. Sorry. And another thing is that you can also decide to focus on, if you're interested in knowing the length, for example, of the season, the duration of the sowing season, the timing of the start of the sowing, or the timing of the start of the heave, or the freezing season, you can extract, for example, the maximum value, the maximum displacement of the season, which is mapped here in the map A, only in flat terrain, so everything else has been removed in this case. But you can also focus on when it happened and map basically the timing of it, which also can be of interest for different users. If we imagine doing that systematically each season, then you can have an information on how it changed between years. Another kind of application is sloping terrain, and I have mostly worked with rock glaciers. That's why I'm presenting some example with rock glaciers, but of course you can imagine using InSAR for different processes. So rock glacier are landform consisting of it's a mixture of rock debris, sediments, and ice that are creeping down the slopes, and they are really influenced by water, ice content, and temperature, which makes them quite vulnerable, not vulnerable, but influenced by climate change as well. So that's why there is a focus in this field in the research community to try to use rock glacier as climate change indicator. And if you imagine if the goal is, for example, to map slope movement, rock glacier or other kind of slope movements, then you can use InSAR to have a rather semi-quantitative information, how much it has moved approximatively, classes of velocities, for example, and assign a value to each identified landform, potentially mapped from before, based on morphological evidences, or of course it can help to identify new landforms. And here it's an example where we have done the work for rock glaciers in Svalbard. And of course, the long-term goal is to also monitor how these landforms are changing, how the movement is changing, and if we can extract time series on, for example, several rock glaciers, then we can maybe provide average interannual velocity rate that could be used as climate change indicator. I think I'm getting slow. Sorry if I speak too much, but we still have time. Good. So now, if we think about what can we provide, and because now I have showed several examples, and obviously we have to choose what will be in this ground motion service, and we cannot do everything. There are also some logistical question, operational question, and limited resources. So we have started to make some test products as part of this Permameteo community project that is led by UNES. And Permameteo community project funded supported NORCE with a little project to make InSAR maps around Longyearbyen. So these are some results that can also be used as pilot products to discuss the future of InSAR Svalbard in the future. And you see, this is the same visualization tool as used in the mainland Norway. So that's the same web portal as InSAR Norway, if you have been in InSAR Norway before. But it's not exactly the same kind of visualization because it needs to be adjusted. So what we see here is the maximum displacement during seasons. So each seasons are processed separately, and we extract the maximum subsidence or the maximum displacement that occur for each of the points where we measure movement. With here, it's in millimeter 0 to 50 millimeter scale. So again, we see that in ice-rich areas, it moves more, and in sloping terrain, you have some rock glaciers or some glacial features that stick out. And then you can also look at time series. So if you draw a polygon somewhere, for example, in this ice-rich region in Bredal, you can visualize the time series for each season altogether. So again, in this case, it's important to remember that each season has been processed separately, so that it doesn't mean that it goes back to the same level. We don't know basically what happened between the end of the season in 2016 and the beginning of 2017. That's something we still have to work with. It may be possible to connect the season and have information on long-term interannual patterns, let's say. But it also depends what the users are interested in. So we have the project to work with this kind of questions in the future. And again, you see subsidence heave pattern for each season in this area that is flat, relatively flat. And if you take a slope slope process, so this is Sverdrup rock glacier in Longyearbyen. You can do the same. You can average this landform, and in this case, I just picked one season to show, but you can also visualize the time series for all the seasons, and you can see how the rock glacier has moved throughout the season with some event with little acceleration, but it's rather linear in that case. Yes, so that was a bit an overview of what we have done until now. So it's important to remember that these are examples of possible products based on past and current projects. But what we will include in InSAR Svalbard GMS, Ground Motion Service, it is still open. And that's why we're also launching this project and wanted to have this webinar, because we want to have your feedback on what can be useful for you. We have to account for technical and practical consideration as well. So InSAR limitation, processing time, resources. But of course, we want to have the best balance. So here I just listed a couple of open questions we have. And Maria will also go further with that just after. But many questions are about which kind of really standard projects we want to have, like the default product at large scale, covering the entire, let's say, Svalbard. Do we want also high-level products, like for post-process product for specific applications, focusing, I don't know, on rock slide, focusing on rock glaciers, etc. Do we want different projects in different areas, more detailed around settlements, research stations? And also a big question is that now we're speaking about ground motion service, because this is what exists also in the mainland. Of course, in Svalbard, when you look at this map here, you see a lot of white glaciers, and it's a natural question to ask, do we want also product tailored for glaciological application? Can we move toward a ground and ice motion service for Svalbard? And this is not something we will manage to provide in this project directly, but we at least can provide pilot products and design the future in that direction. Yeah, so with that, I'll let Maria take over to explain a bit the next steps and what we hope you can contribute to.
Okay, so the work plan from now on is, this is a 3-year development project, where the aim is to agree on a basis for the upcoming ground motion service. The project is divided into 4 work packages. Number 1 is the project definition, where we will connect to and establish a reference group that includes remote sensing experts, researchers that are active on Svalbard, for example, and ask them to help us define these products and technical needs. Based on that, we will develop pilot project and visualization solutions, mainly around Longyearbyen and Ny-Ålesund in the beginning. These pilot projects in work package 3, we will ask for feedback from users and then adjust the product based on the comments that we will receive. And then the final step is to upscale from Longyearbyen and Ny-Ålesund and decide on which selected project that we will provide on the entire Svalbard and deliver them in an open and freely accessible web portal, a little bit like InSAR Norway today. So in time, it looks like this, our work plan. We will have a user workshop now in September, and we'll talk a little bit more about that. After that, we will start producing the pilot project, and then a second user workshop in 1 year time in autumn to ask for feedback. And then comes the upscaling phase towards 2025. So next up is that we would really appreciate your feedback. We have made a user survey. Lynn is now posting it in the chat, I think, or it's also here listed, where we will ask questions like, how do you work with InSAR? What applications are you interested in to use InSAR data on Svalbard? What is the main value for your application? For example, are you interested in detecting and identifying moving landforms? Do you want to understand the dynamics? Do you want to monitor more man-made infrastructure and structures, or do you want to use it for cross-validation to other displacement measurements? And then what type of InSAR project are you interested in? Are you interested in this displacement time series, or are you more interested in maybe the more average maps that documents horizontal and vertical displacement? Or are you only interested in single interferograms? Or maybe all of them. Some of the questions in this survey require a little bit of InSAR background. But if you're new to InSAR and still have some ideas that we might not have thought about and don't know all the technical details, also, I don't know yet, is also a very valid answer. And then we have started to establish a reference group, a group of people that are willing to follow us on this process and to contribute to identify the user needs and requirements and help us to define the products. And then later on also evaluate the pilot products. And what we really would like to see is the diversity of people from different institutions with different backgrounds using InSAR on different applications. So if you're also interested in joining this group and follow us, please write your email in the chat and we will contact you. This first user workshop will be in Longyearbyen, August 31st, and maybe also parts of September 1st, depending a little bit of who's coming and how many and such. And the objective of this workshop is to discuss the results of the user survey and discuss more in detail on the user requirements and specifications that you would like, and discuss possible products and different visualization options that might fit different applications. And the aim is, of course, to find a solution that both fulfill the user needs and also take into account the technical limitation of the InSAR technique. And then, as mentioned, a follow-up user workshop after we have developed some pilot projects in autumn 2024. So that was what we had today to present to you.